No, we always do.
I added a couple of readings. We're going to put the math in Ma270 here for a little while. And we're going to start talking about analysis of algorithms. Mostly, I realize that you guys are working on Huffman right now, but right after this we're going to start talking about sorting. And the reason that in order to get faster sorts, we need to understand the mathematics of how to analyze algorithms so that we can appreciate that this sort is actually faster than this sort. And so I'll start to talk about that a little bit today if I have time, and then certainly for the next couple of class periods we'll talk about analysis of algorithms, and then we'll move into sorting algorithms. So I've added these two links. They're both Wikipedia pages, but I've looked them over and they look fine to me. So there's one on big O notation, and then there's another on analysis of algorithms. And big O notation is a real phrase. If you go into any computer science or mathematics department in the world and ask them about big O notation, they'll know exactly what you're talking about. It is a technical term. All right. What I wanted to do today was I'd like to talk a little bit about testing and the baby steps, in a sense, of getting up to a working Huffman. And then I'm going to, when we talk about the encoding or the compression step, I want to go on a little bit of a tangent and talk a little bit about worst case scenarios, things like that, and then we'll move in if we have enough time. We'll move into the beginnings of big O notation and analysis of algorithms. So if you'll recall, my HZip program we talked a little bit about the various member functions, and again, you are not bound by the structures and the classes and so forth that I'm talking about here. I'm mostly using my code as a vehicle to discuss some of the issues that you're going to encounter no matter how you choose to organize your program. The count function, we've briefly talked about the count function. For me, count goes through and does a frequency count of all of the individual bytes and then sorts them in a linked list. The build tree algorithm is essentially successively taking the two smallest subtrees, joining them together under a new node, and then reinserting the new node, removing those first two subtrees, and then inserting the new subtree. Put header is going to rely on your putInt function from bitstream. Remember, I had you write a putInt function that would take an integer and write it out to the file as a b-bit binary representation. And we talked briefly about that. The root node goes out and is possibly needs 10 bits. So we'll write out the root node as 10 bits, and then we'll write out the left and right children of the remaining interior nodes as 9-bit integers. And that leaves us, that brings us up to the encode step, and that's what I wanted to talk about today. So let me pull up, I wonder if I have an old Huffman tree. Yeah. Okay, so there's an old Huffman tree. Let's talk about how to encode this file. This guy was the file, I think, ABC or something like that. I don't remember. Yeah. And so we're going to go through the input file, the file to be compressed. And every byte that we encounter is going to start us off at a leaf node. So let's talk about that for a second. Oops. So we go through the original byte by byte. All right, and each byte, can't write today, each byte gives a leaf node. Right? So we're going through, say, the file AB, ABC. We hit A, which we know is right here. And what we do is we follow the parent pointers up to the root node. How do we know that we're at the root node if we're following parent pointers? Yeah, I'll get an EOL. Right, so I'll follow the parent pointer, and the parent pointer will become -1, which is our end of list character. So to EOL. And the way it works is I follow the parent pointer. And then what you'll do is you'll compare you'll compare the index that you came from to the left and the right children behind you. So you follow the parent. Let's do a little microcosm here. And we have node 1 and node 2. And so let's say you're coming from node 1 and you're going up. So you follow the parent, and now your cursor is up here. And what you do to figure out where you came from is you look at the left child and the right child of the cursor. And if left child is equal to n1, then you know you came from the left child. If right child is equal to n1, then you know, you get my drift. So you're going to go up, and let's say that you came from we'll look back and we'll check if n1 equals cursor left child, then we'll say the code B is equal to 1, else B is equal to 0. And that's just a matter of how you're counting left and right. So if left is 1 and right is 0, then you'll do that.
Are we giving some sort of previous pointer to that?
Not necessarily. So you can, yeah, I mean, I guess you could do that. You could have a pre-pointer that would be n1. Sure, let's do that.
Wait, well, what else? Just look at the last.
It's just a matter of, I mean, just saving n1, which is essentially a pre-pointer.
Okay,
So
okay.
yeah. And yeah, let's call it prev. I like that. So you're at prev, and you look at, but prev is really just an index. Okay. And cursor is just an index In fact, really what we're doing here is something like node array prev equals node array cursor dot left child. And if it doesn't match the left child, it must match the right child, right? Because you came from one of the children. You followed the parent pointer. So if it doesn't equal the left child, it has to equal the right child. Now, you do this all the way up. So you follow this all the way up to the root node.
And we do this little algorithm at any time we move on one, as opposed to just going to the root and then looking all the way back.
Yeah, so I'm sort of building up to this, right? What do I do with that B? I would love to be able to do that.
Oh, we need to reverse everything?
I would love to be able to just dump B out to the file, but I can't.
Yeah, we need to keep it in a buffer, don't we? And
Yeah,
then
we
flip
actually
the
have to
buffer.
save the code. So we actually have to generate the whole code for the character. So, excuse me. So what that means is I have to save this guy in some kind of array. We have to store the bits of the code for this character, or this byte, in an array. And then after you reach the root node, then dump the bits to the file in reverse. So why is that? Why is that the case?
Because we need the path down as opposed to the path up.
Why?
So you're traversing the tree.
I mean, I'm not compressing this file just for the hell of it, right? At some point I want to decompress it. And the only way I'm going to be able to decompress it, as I think you both are getting at, is to start at the root and go down. Because if I start at a leaf, the code doesn't really help me. It doesn't tell me how to go. All I can do is follow parents all the way up. So I need to dump them in reverse order so that I can decompress. So in some sense, the information, if I didn't reverse it, the information for these guys would still be there, but it wouldn't really be there in a useful way. I wouldn't really be able to get it back out. So I have to dump these bits to the file in reverse order and decompress, for decompression. My question is, and this could last 5 minutes, it could last the rest of the time period, is how big does that array need to be?
256.
Why?
Because that's your longest path for your smallest.
Worst case scenario, right, is I start at a leaf and its parent is 257, and the parent of 257 is 258, and the parent of 258 is 259, all the way up, right? That's worst case scenario.
How would that even be possible?
Well, let's talk about that. So worst case is I go leaf, and then parent is 257, and the parent of that guy is 258, and so on, all the way up to, what's the last parent? Let's not make that mistake again. 512. And that was. Now, I have to store a bit for each one of these guys. So there's B0, B1, B2, all the way up to B, say N. And Evan's claim, and it's correct, is we need 512 minus essentially 256 slots in that array, possibly.
So that means that we can have a code that's 256 bits long for one character.
It does. Can anybody think of when that might happen?
Got a really terrible tree that goes like.
So how do I get the terrible tree?
I was trying to think of that. I think you need an incidence rate that's sort of like a Fibonacci, but like one more. So you get 1 and then 1, and that's still less than 3. So then that pairs up like this. And
So let's do it. 1, 1, 1, right? And then I join these two guys together and I get 2, right? And what I want to do is keep that at the front of the list.
So even if you had 2,
So 2 here, and then I'll join those two guys together and get 4. And I need to keep that at the front of the list, right? So 4, and I've got 8 up here.
okay, so it's 2.
So it's powers of 2. Now, if the byte frequency, if I have this weird byte frequency, so here's the 0 byte, here's the 1 byte, here's the 2 byte, the 3 byte. Yeah. Now, this goes all the way up to, how many different bytes are there? There are 257? 7.
You have.
257.
Okay, and the pattern here is,
Wouldn't there be like 255, but then be still the end of file?
No, because there's also the 0 button.
no, you're right. It's 256, yeah, 257, yeah. Let's not do this again. Okay. This is 2 squared, right? The next one will be 2 cubed, and so on. So this guy is going to be 2 to the 256. So that means that last byte has to occur 2 to the 256 times. It's a big number, right? Not only that, this file has to have plus all the characters below it. So we're talking about 1 plus the sum, say I equals 0 to what, 256 of 2 to the I?
So it would be 2 to the 257.
Anyone got that
minus
TI 89?
Good.
I don't think that.
So that's 1 plus 2 to the 257 minus 1, which is 2 to the 257. Is that right?
Oh, yeah.
How do you put this in magnitude?
Do people know this identity? Here, let's do that identity.
Shirley, just really quick, I'm probably crazy. We have 257 bytes, right? And aren't those array indices, so wouldn't we only go up to 256?
Yeah, that last one.
Yeah.
Yeah.
Or would we?
Yeah, 0 to 256.
So this is 255 right here.
Yeah.
Yeah.
Thank you.
Okay.
You did have to do it again.
We did, didn't we? So this is 5. So this is 5. This is actually good because this is what I had in my notes, and I'm like, what the hell? 2 to the 256. Let me just walk you through that identity. So if I want to sum up those guys, let's call that Sn, and this is something that you're probably familiar with. I can multiply this by 2. And then I can subtract the top line from the bottom line. If I subtract the top line from the bottom line, I get Sn, and I get 2 to the n plus 1, and then a minus 1 down there. And so what I see, and that's secretly the sum I equals 0 to n of 2 to the I, right? So if I focus on this bit here, I see that that is precisely the form that I have here, where n is 255, And so what is this, 256 right here? Yeah. So I apply the formula with n equal to 255, then this guy is 2 to the 256 minus 1, which is that part right there. I have an extra 1 in there, which happens to cancel nicely with these two guys. And so I would need, just to achieve worst case scenario, I need a file with 2 to the 256 bytes in there. If anybody's connected to the net like me,
It's 10 to the 77, 2 times 10 to the 77.
have you ever heard of the Eddington number?
The leading name for the most significant digit in this number is quattorvigintorian.
Am I not? What is the deal here? Why must my network die? I got nothing. Somebody that actually has internet access?
Yeah.
Eddington number?
Yeah.
What is it? And what is it?
Which was 136 times 2 to the 256.
Yeah, so this is a fair portion of the number of protons in the observable universe. You're less than likely to actually encounter a file that large. And there are other impediments that you're going to run into before you run into this particular issue. Computer space. Sure. Let's pretend that you had enough space in your computer, and yet you were using. There's one really huge limiter that cuts you off well before you reach this.
Oh, the bits on your processor.
If I'm going to do frequency counts, right? I'm counting all these bits. That last one has a lot of it occurs quite often. And where am I storing the frequency counts? In an int, right? At best, it's an unsigned int, which is 2 to the 32 in our case, right? That gets you a whopping, not even close, right? That gets you like 4 billion or something, 2 to the 32. So you're going to run out of steam in this example long before you get here. So it kind of gets, this is an interesting question. How big does this array have to be? It clearly my frequency counts are going to run out before I get to this really bad situation. So let me make a note of that in here while you think. So we can't get here.
What if we made like a super high dimensional array
Oh,
to store the frequency?
yeah, I'm not saying that you can't that you can't improve this. What I'm really trying to get at is how big does this array need to be, given that we are going to count with unsigned ints? Oh, I know it's going to take 257 unsigned ints to do the frequency count, because I only have 257 different bytes that I'm dealing with, and not even, right? There's the one fake one, but. So I know I need 257 unsigned ints to do the frequency count. But what I'm worried about is how long does that bit array need to be in order to ensure that I'm going to have enough space for the longest code.
If we're past 32, we're probably already screwed. then if we didn't write our program with reading in longs, you're not going to be able to actually read the full.
So this frequency count, right, in our case, can't exceed. It can't exceed 2 to the 32, and we're just speaking loosely here, but right, that frequency count can't exceed 2 to the 32. It actually is. There's even another limitation, right? Because ultimately, all of those frequencies get added up, and what's the weight of the root node?
The sum of frequencies.
The number of characters, right? So we're really limited. Even a particular character can't go that high. Right? We're limited by the weight of the root node, which is 2 to the 32.
So,
anybody? Yeah.
So at most we could have a frequency of 2 to the 31, right? So then we need 32 bits.
Yeah, because then yeah. I mean, you need probably less than that, because when you sum up all these guys, I guess what you need is, you've got to figure out, like, you've got 257, which is what, roughly 2 to the 8th, right? And then let's see, 32 minus 8, 24, like 2 to the 24th in each slot, roughly. So if you have 2 to the 24th in each slot, and then you multiply that by 2 to the 8th, you're at 2 to the 32.
2 to the 24th, isn't that still way beyond what your hard drive space is like?
No, that's not too bad, because 2 to the 32 is 4 gigabytes.
Oh, okay.
2 to the 32 is 4 gigabytes. So 2 to the 24 is actually within the realm of possibility. So you could overflow your Huffman on a regular file, a file that you have access to that wouldn't take an infinity to run.
Just like a movie on your hard drive.
Right, and if you remember I pulled up the gzip thing, the gzip description. Let me go back to that.
Speaking of YouTube, I don't know if you noticed, but you uploaded the 160s, or the 160s.
Today?
Yeah.
Yeah, I fixed it.
Okay.
Thank you, though.
I saw it earlier and I freaked out. I was like, wait.
Since the weights don't have to be exact, right? We don't really care if they're exact or not. We just want generally which ones are more frequent. Can we just use doubles and throw this problem out the window? You don't actually care. We'll lose a little bit of precision.
So one of the things I haven't done yet, but I will do probably after break, is prove that Huffman is optimal. And you can't really prove that Huffman is optimal if you just kind of fudge it. And we laugh, but you could, then you don't have the kind of assurance that this is an optimal compression, that you're getting the best compression. If you're sort of just, it's kind of sorted. You could introduce some bad behavior that's unintended. I think you're probably right that it wouldn't, on average.
But if you're still working within integer precision, then a double will give you enough decimal points to accurately portray which weights are bigger than others. And then it only helps when you go out of integer.
No, because remember that a double's only carrying 16 digits of precision.
Right.
So when you get down below that, you're mushing stuff together. You're not reliably sorting.
But down below that, aren't you already out of integer precision anyway?
So let's say you have I'm not sure how it would fail, but at the very least you've got a lower bound of 1. So there's one character that occurs once. And then you've got another character that occurs I'm trying to build an example and I can't quite pull it off. I have to think about that. Anyway, and I'm not going to pull up the gzip because I'm not finding it here, but you'll remember that the gzip thing worked on 32K chunks. Does that ring a bell? That's why. Or it's one of the reasons why. So it would do a Huffman compression on a 32K byte chunk, and probably part of that was just due to let's not risk having overflows. Because
so that means it's re-encoding the tree after each chunk.
Exactly. So it takes a 32 kilobyte chunk, does a Huffman tree compression on that, and dumps it out. Now, what's the cost of that?
You have to store more Huffman trees.
I have to store a bunch of Huffman trees instead of one. That's not too bad of a cost, though, right? Because the Huffman trees are pretty small, relatively speaking.
And then instead of like the end of file, you're gonna have like end of chunk.
Yeah, exactly. And that's a cheap and easy way around this problem, rather than building some massive integer that can go much further than a traditional int. Just break it up. Yeah. We still haven't quite answered the question, though.
Is it 33 size array?
That's what I think.
Based on pattern observation?
Yeah, because the deepest tree that I can build is like around 32, 33. The thing I haven't answered, and maybe you guys can think about this over break, right? I've got this pattern that I've used to build a deep tree, right? But let's say that my frequency count is limited to 2 to the 32. If that's the case, then I can make the tree like 31 deep, right? Now I'm not allowed to use characters that occur more frequently than that. I'm only allowed to throw in characters that occur less frequently than that. Can I make a deeper tree? And that's the answer. The answer is I don't know. I'm sure the answer is out there, and I intentionally didn't go out and look for it. If you want the answer without thinking about it, you can probably go search. Google for something like worst case Huffman tree, and get lots of information about how to build worst case Huffman trees. But I want to keep thinking about it a little bit before I go there. I thought I'd share that with you guys. So. That said, how big are you going to make your bit buffer for the code? 256. You're guaranteed that it's not going to be longer than that. And it's only 256 bytes, so who cares?
All that.
But this is the kind of thing that a theoretical computer scientist thinks about. And it's math. It's really just math. And there's some hard questions that you run into in computer science along these lines. This is actually fairly simple. It's probably quite well understood, but we're just such novices that we can't think about it right off the bat, Jamie.
So then, if the bit buffer is like 255 or something massive, then I mean when we then throw that into the header, when we actually do the compression, what will happen? Because we'll have all of those padded zeros, right?
No, we won't. Okay, so we're going to keep track of how long the code is as we go up the parent pointers,
okay.
And we're only going to write out the piece of it that's meaningful. But we give ourselves enough slack in the buffer that if we get this case, we're going to be able to go all the way up.
So just like throw a -1 in there at the end or something.
But what I strongly suspect is that a bit buffer of around 32, 33 is going to suffice, because we're going to run into frequency overflows before we run into the bit buffer overflow. So you'll go up from the leaf to the parent, and you'll keep track of the left-right child, zeros and ones, and you'll write them out to this bit buffer. And then when you get to the root node, before you go and do the next byte, you're going to take that thing and you're going to write it out from top to bottom out to the file using what? Putbit. And when putbit is done, then go back and get the next byte, go to that leaf, work your way up to the root, buffer those bits, write them out in reverse. And do it over and over and over again until what? End of the file, actually. This is the compression step. And then when you're done with the end of the file, what's the last thing you have to do? So you've encoded all of the bytes. Don't forget to throw that EOF byte in there, right? Because the decompression program is going to need that in order to know when to stop. Got it? Okay. I was just really surprised when I was thinking about this how the Eddington number was also 2 to the 256, and so I felt like I had to bring that in. Let's talk about big O notation.
Just super fast.
Mm-hmm.
So oh, no, never mind. Okay, we're using put bit, and so it'll actually be putting in a single bit, so we'll have it, and it won't actually be 255 bytes. So
Yep.
for a second, I was like, wait, this is not even close to compression.
Well, and that's the reason you write bitstream, right?
Yeah,
you don't get real compression unless you are able to write single bits. Big O notation. So we will say, here's a definition. Let f and, in fact, a bit of an abusive notation. Let f of n and g of n be functions of n, which is a natural number. Remember what natural numbers are? Just 1, 2, 3, 4, 5. Yes, and 6. But not 7 or 23. So those are the natural numbers, the counting numbers. So we're going to let f and g of n be functions of natural numbers, and we will say that f is big O of g if there is a natural number n. I'm not writing my natural number sign very good here. If there is a capital N in the natural numbers and a constant C positive such that the absolute value of f of n is less than C times the absolute value of g of n whenever n is bigger than big N. And we actually use the equality sign. We say f equals big O of g. And that's kind of part of the definition. It's not something that you would normally, it's not a place where you would normally use equals. But it is the case. Let me give you an example so that you can kind of parse this definition. I recognize that it's complicated. Let's consider just a simple function, a polynomial function of n. And let's look at g of n is just n squared. Okay, it is the case that f is equal to big O of n squared, or big O of g, you might say. It is the case that f is big O of n squared. But let's see if we can prove that. So we write 3n squared plus 2n plus 4, and we take its absolute value because we're interested in the absolute value of f. And we use a well-known inequality to write it like this, the triangle inequality, although in this case everything in sight is positive, so it doesn't really matter. But I just want to get some of these tools out there in front of you so that you can see that. And some more manipulation. In fact, I guess that's an equality. Here's a less than. So how do you read these things, these inequalities, these stacks of equations? This guy is the relationship between the left and the right. This guy is the relationship between the top line, the top right, and the middle right. And this is the relationship between the middle right and the bottom right. And that's how these stacks of equalities and inequalities work. How is this useful? Well, by transitivity, this guy applies to these two as well. And that's kind of where I'm headed. And you see this device used in math books all the time. Now, that third inequality, the one with the double circle around it, how did I get there? What did I do? What manipulation do you notice?
Multiplied by absolute value of n a couple times, but only with certain terms.
Yeah, so I replaced n with n squared. On the natural numbers, that only makes it bigger, right? And on the last guy there, I had 4, and I just threw in an n squared. And again, for natural numbers, that only makes the right-hand side larger. Why is that useful? Well, it lets me get to the form of the definition, which is 9n squared, something like that. And this is true for any n bigger than or equal to 1. So there's the capital N that I refer to. Here's the constant c. And we can say now that f is big O of n squared. And this is as n goes to infinity. I should have noted that up here. There's an extra thing here, as n goes to infinity. In computer science, this is largely used to compare growth rates. Yes, Jamie?
Is C also in the natural numbers?
C is any real number positive.
Okay.
Any real number positive. Often we'll say R plus to indicate positive real numbers. This is used to compare algorithms. For example, let's talk a little bit about a simple for loop. Let's talk about for I equals 1, I less than or equal to, let's say, n. Let's use little n. I plus plus. And let's say that we just do something like sum equals 0, sum plus equals I. And what I want to do is estimate the runtime of this loop. How long does it take the computer to run this loop? Well, that's a tough question because clearly it depends on your equipment. So what you're going to do instead is kind of have this pretend abstract computer that, say, takes, maybe it takes C1 amount of time to do that. What other calculations are going on in this loop? So there's some more stuff here, C2 time to do that. What else? Yeah, the check. That's C3 time to do that. And we assume that those 3 times are about the same no matter what the values of sum and I are, and n. Right? We assume that those things take about the same time. And that's a fairly safe assumption. And then I guess there's this guy here that takes also a little bit of time, this assignment. Sure, we could throw that in there too. So C5. Now, how many times does C5 happen? So we'll get the total running time here as a function of n, say. The total running time is 1 C5. How many times does C4 happen? How many times does C3 happen? N?
Actually, I think n plus 1. Unless.
Well, we're
Yeah,
starting
n plus
at
1. No, but it does one check before it breaks out of the loop.
Yeah, that's true.
Good. C2? And C1?
N?
All right, so we have a bunch of stuff here. Some of it depends on n, some of it doesn't. What I'm going to do is lump some things together. So I'm going to take all the stuff that depends on n and lump it together under one big constant, say c, and all the stuff that doesn't depend on n and lump it together under a constant, say d. If we take the absolute value of Tn, that's clearly less than or equal to, say, C plus D times N. Agreed? And so we can say that Tn is big O of what? Of N. What if I take this guy, I'll take this loop and run it twice. Oops. Should use J. Grr. Yada, yada, yada. You know what I'm talking about? Okay, so in here, we just did this one. This is Tn. And the outer loop forces me to do what? It does it twice. So how long does it take to run this guy? 2Tn. In the land of algorithms, they cost the same. All right, running this thing twice versus running it once, as n goes to infinity, we don't care. It's the same thing. So this is still big O of n. Because Tn plus Tn is really big O of n plus big O of n. And big O of n plus big O of n is big O of n. We can prove that. You can think of big O of n, so we see, let's do T2Tn. That's less than or equal to some constant times, well, let's start with T of n, sorry. That's less than or equal to some constant times n, right? Multiply both sides by 2. And one positive constant is as good as another positive constant. And so this is still big O of n. Jamie?
So do we have to go through it n times before it turned into something different?
Different, yeah, exactly. If I run through this any fixed number of times, yeah. But if I introduce growth in n, right, if I introduce dependence on n, then things change. We'll talk a lot more about this on Friday. But there's a bit of an introduction. All right, see you then. You'll like big O notation. You can just not care about the details at all.